Hybridization. Okay, this section will be all about hybridization. Hybridization is the idea that atomic orbitals can fuse together to form newly hybridized orbitals. These hybridized orbitals can have an influence on the molecular geometry and the bonding properties. Hybrid orbitals can be very useful in the explanation of molecular geometry and atomic bonding properties and are symmetrically disposed in space. Although sometimes taught together with the valence-shell electron pair repulsion theory, valence bond and hybridization are in fact not related to the VSE-PRT model. Now, there are three main types of hybridization, and we are going to look into these in more detail. Sp3 hybridization occurs when a tetrahedral molecule is formed. The central atom, let's use carbon as an example, will have 4 electrons in its outer, as seen in the ground state of this diagram. However, there are only 2 unpaired electrons available for bonding, so this cannot be the orbital structure for tetrahedral molecules such as methane. An excited version of carbon's electrons could allow 4 bonds to form, but they are at different energies, and the orbital with the lowest energy must be filled first. Therefore, hybridization is necessary. This mixes the 2s and the 2p orbitals to form 4 sp3 orbitals. All 4 of these orbitals have the same energy, and so the 4 carbon-hydrogen bonds can be formed. Let's have a look at what this is in a diametric format. As you can see here, the s orbital, coloured purple, can bond to the 3 of the p orbitals, coloured blue, to form the 4 sp3 orbitals, coloured green. It is important to note that despite CH4 having 4 bonds, NH3 only has 3 bonds, but NH3 still exhibits sp3 hybridization. This is because there is a lone pair on the nitrogen atom. 3 of the sp3 hybridized orbitals are used to form NH bonds, and the 4th orbital is used to hold the lone pair. Sp2 hybridization occurs when a trigonal bipyramidal molecule is formed, or when a pi bond is present. An example of this would be a COOH functional group. The carbon is still forming 4 bonds technically, but one of them is a pi bond, although it doesn't affect the shape. As it is effectively only forming 3 bonds, the shape will be trigonal planar, with a pi bond perpendicular to the plane of the molecule. Again, however, the electron configuration prevents this happening, and when excited, the 2s orbital still needs filling first. So the orbitals are hybridized, but only 3 sp2 orbitals. Because the sp2 orbitals are lower in energy than the remaining p orbital, they are filled first, thus creating the correct geometry for the functional group. Once again, let's have a look at what this is in a diametric format. The s orbital, coloured purple, can bond to the 2 of the p orbitals, coloured blue, to form 3 sp2 orbitals, coloured green. However, there is an exception in BF3, a trigonal planar molecule with no pi bonds. The final type of hybridization is called sp hybridization, and it occurs when 2 pi bonds are formed. An example would be a cyanide functional group. The central atom, carbon, still has 4 bonds in its outer shell, as seen in the ground state of this diagram. However, there are only 2 unpaired electrons. While this seems fine for a cyanide functional group, there is a triple bond to the nitrogen atom, so there should be 2 unpaired electron p orbitals, which there is, but also the other bonds for the sigma bonds to the nitrogen atom and the rest of the molecule. Again, hybridizing the orbitals to form hybrid orbitals is the solution. In this case, there are 2 sp orbitals and 2 p orbitals for the triple bond. The nitrogen, in this example, has a triple bond to the carbon, so is also sp hybridized. Let's have a closer look at the orbitals. The s orbital, coloured purple, can bond to one of the p orbitals, coloured blue, to form 2 sp orbitals, coloured green. There is an exception to this. CO, which has charges.